Hello, everyone. I hope you're having a good day, and we want to thank you for joining us at TigerGraph's webinar today on accelerating machine learning with graph. We have a program that's about an hour and a half long today. We'll be demonstrating several uses of TigerGraph. So my name is Victor Lee. I'll be hosting today, and I'm joined by two of my colleagues, John Herkey and Manil Shah. I'm going to go through some of the logistics first before we get into the content. So we are using Zoom. Your audio is muted, but if you have any questions at any time, you can use the Q&A tab in the Zoom. There's also chat. So we'd like to sort of separate Q&A. If you have a question for the presenters, in particular, we will have Q&A sessions at the end. Though those of us that are not speaking will be trying to monitoring during the presentation. If you have any technical issues, you can send those in chat. And this is being recorded, and you will get a link to the recorded slides and webinar shortly after its conclusion. So as I said, my name is Victor Lee. I'm head of product strategy and developer relations, and I have a background in graph algorithms and graph data mining. John Herkey, we need to change his title. He is manager of developer relations, is with us today, and he has a lot of experience working with developers and building community and sharing the TigerGraph with that community. And Manil Shah, one of our solution architects, will be also doing a demo. So we'll have a three-part demo here today. And so this is the agenda. I'm going to get you started with showing you how to sign up for a free TigerGraph Cloud account and to get started with a new instance. And then I will go into unsupervised learning with graph algorithms. Then I'll hand it off to John. He will talk about graph enrichment and feature extraction. And Manil will conclude with showing you in-database machine learning techniques for graphs. So graph and AI, that is a great combination. It delivers more value and better results than either alone. Now, the graph data model by itself really shows you how things are connected in the real world. And in that sense, it's providing you richer data. It's modeling things more closely to how people actually think about them. And it allows you to show more relationships than you would with a tabular type of data structure. And it makes it very easy to join different data sets because all you need to do is make links between them, which is already a native part of the data structure to have links from one type of entity to another. You can then ask deeper and smarter questions because you can have semantic types of relationships, such as a customer resides at a location, a customer purchased an order. Again, you might expect these type of things in other databases, but realize how unlimited you are in setting up as many relations. You don't have to create a new table, you just create a new link. And because of the very natural and visual model, this will actually help you to see more questions that you can ask. You actually realize, oh, I can ask that question. And because of its performance characteristics of following connections very fast, very efficiently, you'll be able to ask more complex questions and get those answers in real time. You'll have more computational options. We're going to go over graph algorithms. I'm going to go over graph algorithms today, and my colleagues are going to go over graph enhanced machine learning. And the benefit of graph enhanced machine learning, or just even more basic analytics and queries, is that you get explainable results. And that, again, that goes to the data model. The data model itself is very explainable. You can look at this picture and see what it's saying. And so when you train your machine learning model based on graph features, and so your model is expressed in terms of the graph features, it's inherently explainable, and it's also very visual. So I'm going to get into part one, graph algorithms for unsupervised machine learning. There are several types of machine learning, and we're going to be focusing today on the two basic types, unsupervised and supervised. And the key difference is whether it uses labels or not. And what a label is, it's a classification or group name. So it's the name of a category or a group that you can put on some data items. Like, for example, you can label foods as kosher or not. You can, again, you can label transactions as fraudulent or not. That's a label. When you have unsupervised data, you don't have any labels, or you haven't designated any. You may have attributes. You may know those things, but you have not selected them as sort of your target classification. You're not aiming to classify things based on the labels. They're maybe just part of your data. In unsupervised machine learning, what you're trying to do is you have a more open mind, and you're asking the data, show me your intrinsic patterns. Tell me what is characteristic about yourself as a data set. And in that sense, you want to gain insight. For example, clustering is an example of unsupervised learning. Show me where there are natural groupings of data. Show me what is a common pattern you see. Show me what is an unusual pattern or an outlier that you see. And so you're not giving it any targets about what the answer should be, looking for these natural groupings or natural correlations. That association rule mining is, again, talking about correlations maybe between one variable and another. In supervised learning, you do have some labels, and you're aiming to predict the labels. You know the labels on some data, and you either have, you now have some data, or you will have future data that is unlabeled, and you want to use the currently labeled data to help you predict what should the label be, what is it likely to be on some other data. And this falls into two major categories of classification, when they are discrete variables, or regression when it's more of a continuous number. And then there's some variations, semi-supervised and reinforcement. And we're not going to have time today to go into those types. We're going to focus on unsupervised and supervised learning, the two major categories. And we're going to be using TigerGraph Cloud, tgcloud.io. We have a get started video, but I'm going to just walk you right today into how to create an account, how to deploy an instance, select a starter kit. You can use the free tier, which is, you can use TigerGraph Cloud for free. If you need a more powerful machine or a larger machine, you can pay for just what you use. And when we do this, if you may be able to do this as in following along, remember the URL and password. You'll need that in the future. So let me jump right into that. I'm going to switch to tgcloud.io, and I'm already logged in, I think. So this is where you would register. This is good. I am registered already, so let me quickly sign out. And again, so this is what you would see. You can choose to use an existing Google account or a LinkedIn account. So you click sign up. So again, it would ask you to fill in this information. I'm going to assume it's just a very standard form. So we will jump to the logging in. And so this is your dashboard. It tells you, this is historically how many times I've started a solution. I don't actually have 68 active ones. How much I've spent. If this were a brand new account, you would have $25 of credits. I've used mine up. Again, it tells you some statistics, but we want to go to solutions. This shows that I have one that's ready to use. That's the one I'm going to be using today, but I'm going to walk you through how you would create a new one. So in the upper right, click the Create New Solution. You have your choice of using, currently we offer two different TigerGraph versions, our 3.0 series or our 2.6 series. Might as well use the newer one. And I'm going to want a graph algorithm instance. And the one that I'm going to use for today's demo is Centrality algorithms. We have a total of about 25 or 30 different starter kits you can choose from, or a blank one. And you have choice of running on AWS or Azure. And very shortly, you'll be able to select Google Cloud as well. I already have one free instance in operation. You're allowed to have one free one. So I'm going to show you how you would create a paid one. I happen to be in the Eastern US, so I'm going to select Northern Virginia. And you can, again, select how much disk size you want. And you could also select replicas if you, partitioning. Partitioning and replication, two different things. If you have a large data set and you want a distributed database, you can select any reasonable size up here. Standard is just one instance, no replicas, but I could say I have a lot of data. I want to spread it across 5 machines, and I want 3 replicas. I'm just going to pay 3 times 5, 15 times as much as I would pay for a single instance. Name your solution, Centrality, tag your solution, set up a password. Again, remember this password. Now, it's also going to give you you can pick a subdomain or URL. It's going to be under .io.tigergraph, .i.tgcloud.io. I'm not actually going to create this one. I am description, demo. So I would remember that URL. I would remember that password, confirm all this information. I'm not actually going to kick this off, but that's what you would do. And it would just take you a couple of minutes to start. As I said, I have one that's already done, so I'm going to go to that. Graph Studio. This is sort of statistics, monitoring of your system, and this is the user interface, Graph Studio. Again, I need to log in. It's saved the password. This is your main menu. What here on the left is mostly replicated over here. It's listed in the order in which you would do your normal design flow. First, you design your graph schema. You describe how you want to map input data into the graph. Now you can actually take an external data file and load data. And now you have, once you've gone through those 3 steps, you now have a graph database with data. You can either do ad hoc exploration. You could use our new visual query builder to build graph patterns, drag and drop, or you could write queries in our query language. Now, let's take a quick look at what we have. Because I used a starter kit, it's not empty. There's already a data model here. So this is a flight route data set, which I got off from the internet. This is the published commercial flights from a few years ago. There are some 8,000 airports in here. They each have an ID, a name of the airport, city, country, IATA code. That is, for example, SFO is the IATA code for San Francisco, ORD for O'Hare Airport in Chicago, JFK is John F. Kennedy Airport in New York. The latitude and longitude, and the last one I added score, because we're going to be running some algorithms. Some of those algorithms, the result will be a value that you assign to a vertex. So that gives me a place to put those output values that we calculate. There are then two of these links. They link from an airport back to an airport, and that's the flight route. So there are two versions because this one is undirected and this one is directed. You see this arrowhead. So this means we're going from this airport to this other one. This represents all airports. And later, this is not the actual graph data. This is the schema. It means that there's these three types of things. There's an airport, there's an undirected flight with a miles parameter. How long is that flight route? And a directed one, which shows a reverse edge. So if you want to travel in the opposite direction, it's called reverse underscore flight underscore 2. It also has miles and also shows how many numbers of flights, but we're not going to be using that today. Now, it turns out that I actually have a newer version of this than the current starter kit, and I want to load that newer version. So what I'm going to do is I'm going to go back to the top. And we have here import and export solution. So what I'm going to do is I'm going to get the solution that I want. A solution is a package. It's the TigerGraph Cloud setup. Let me just quickly go to this and then I'll explain what it is when I get there. So I'm going to github.com/tigergraph/ecosys. Oops, shoot. Why is that happening? I misspelled. I'm a lousy typist. Excuse me. And this is a demo. So I'm going to go to demos. And this is part of our Graph Guru series. So under Guru scripts. And this particular one is centrality algorithms. So Guru 27. And under here, I just uploaded this today. Export accelerated machine learning with graphs, algorithm demo. So if I download this file, okay. And then I import it. Now it says it's going to overwrite existing things. And what is it going to overwrite? It's going to overwrite the graph schema, the data mapping, and the queries. And those basically define what we have in our starter kits. There's one more thing, the actual data. The solution files do not include the actual data. The data that I want was included in the starter kit, and I actually want to continue to use that data. I just want a different schema and different queries. And while we're waiting for that, actually, I have not gone over many of these slides. So let me go over the slides. So I said, we're going to be doing some graph algorithms. Those include several categories. There's basic shortest path algorithms. There are clustering algorithms like we talked about. And there are also ranking and centrality algorithms. Interestingly, PageRank is obviously a ranking algorithm. There are also centrality algorithms, which I'll have an example of that in a moment. And then there are finding frequent patterns. We talked about that as a type of unsupervised learning, and similarity. Oh, I mentioned similarity twice. So we'll be doing examples of all of these three types today. And I said we are using this centrality starter kit. And this is where you can go to get that updated file. This is the previous update that I used. And I have, the one I'm using today is essentially the same, but I've streamlined it to include only the things I'm going over today. If you use this one, it'll be more complete. It includes more algorithms. So you might want to get this one. I'm using a streamlined one, as I said, that only includes what I'm doing today. So let's talk for a moment about shortest path. So when I first wrote this, I was talking about airline travel. I know a lot of us have not been doing airline travel recently, but it's a great way of thinking about shortest path, because you have airports and you have the routes between them, and you might be interested, okay, how do I get from city A to city B with the fewest connections? That is a shortest path. It's called an unweighted shortest path, because you don't care what the distance is, you just care about making the fewest connections. So to get from A to H, we can see that there are two different ways that you can get there, with 3 hops and 2 intermediate transfers. So 2 different paths, this upper one and this lower one. Now, if you care about the distance traveled, then interestingly, this one that goes down to D, A, D, C, F, H, is actually shorter, because this 80 plus 90 is less than that 200. So that's called a weighted shortest path. I think I set the numbers so that both this one and the, I think both this red one and blue one are the same total distance. That may not be true. I think the red one is shorter. So that is shortest path. This is centrality. I said I would mention centrality. Now we're again talking about trucks, and let's say we're trying to decide where's the best place to put a distribution center. And you want it to be centrally located. It's even in the name, distribution center. And maybe your concern is that the distance, the average distance to the destinations, where does it have to make deliveries to? Maybe you want that average distance to be the smallest. And that would be, I believe, what we call closeness centrality. And if you had a slightly different question, let's say you want where's the best place to put a gas station such that people pass by it very often. Then you want what's called betweenness centrality, where you sit along the most routes from one place to another. So those are both standard algorithms. They're both in TigerGraph's GSQL library, betweenness and closeness centrality. And let's look at one more example of a graph algorithm. And this one is called, is going to take a more holistic problem. We're looking at medical providers and patients, and who is the most influential medical provider. And we can use PageRank to see which doctor is receiving the most referrals from one doctor to another. And then we could use a community detection algorithm to see who are they making referrals to, not just in one hop, but within a couple hops. And so I know it only took like 30 seconds for my solution to load. So I know my solution is ready. So let's go back to this solution. And I need to speed up, so I give my colleagues some time to work. So design schema, it looks the same as before, but this is the global schema. If I click this globe, I can see that there is a subgraph called mygraph, and you'll see that an additional edge has been added from airport to airport, and it's for similarity, and because I'm going to be running a similarity algorithm. And if I go to here, I see these are the 2 data files where I'm getting my data from. And now I need to load my data. That will take just a few seconds. I click this white button up here. This will take about 30 seconds to load the data. And this gets updated every 10 seconds. See, so far it's loaded 4,600 vertices. They're all airport vertices. And I think on the next update, this is actually all the data. So there's 7,900 airports, a total of 94,000 edges, divided among these directed and undirected edges. So let's now go to our queries. And I have these 5 queries. When you first load a new starter kit, you need to install your queries. So the install button is here. confirms I want to do that. Again, this will take about 2 minutes. So I'm going to go back to my slides for a bit. Actually, I was done here, but let me talk a little bit more about this. So again, the PageRank is what we call a full graph computation, because you're ranking every single node. It needs to look at every single node, and it needs to look at every single connection between them. But it's actually a fairly efficient algorithm. Lots of graph platforms can do PageRank. TigerGraph, you can write the graph algorithm. Let me quickly show you. That's the other thing I wanted to do. I'm going to show you the graph algorithm library. So github.com/tigergraph/graph-algorithms. And we have the algorithms here. And the ones that I'm using today are within this schema-free area. You can see betweenness centrality, closeness centrality, cosine similarity, cycle detection, etc. There are about 30 here. There are a couple more in this template one. And some of these are the more complex ones that require a little bit more effort on your part to use them, but they're more powerful. So that's still loading. And again, the ones that I wanted to show you the PageRank algorithm. There it is. It's mostly comments when you get to the actual code. Interestingly, that's the core of the algorithm. That's comments and some declarations. And this is a whole output for you to choose. We give you three different ways to choose how you want the output. But those are all the lines of code for the PageRank algorithm. The thing is, it's open source and you can modify it. It's if you're familiar with the pseudocode for the power method of PageRank, you should actually recognize this. It's not that hard to learn the GSQL language. And that's actually a great way to start to learn GSQL, by looking at simple algorithms that you know and comparing the GSQL. And of course, we have lots of online tutorials. So I'm hoping this will finish up very quickly. This is, I said, the free instance. It's the least expensive. It's therefore the lowest performance of the instances. If I had used one of the paid instances, this would have happened faster. So I have my various algorithms. The first one I want to do is actually, it's called add weights. And this is one is specialized for this starter kit. What it's going to do, it's going to use what's called the Haversine formula to calculate the distances between airports using their latitude and longitude. It understands the spherical nature of a globe and the sort of odd way that latitude and longitude are numbered. And that's because the source data did not include the distances between airports. It merely just said that there is a route between them, but it didn't tell you, oops, this is supposed to be the edge type. So the edge type is flight 2. And I'll run it for the other one, also flight route. And so now this has calculated the distances between airports. If I were to pick 5 random airports and double click one, oops, nope, nothing there. Oh, why is it not showing the connections? I'm not sure what's going on there, but let me go back here. Let's double check this. So I'm going to run PageRank, and what this is going to do is find the so-called most influential airport in the world, and we'll look at the results to sort of understand what that means. So PageRank uses directed edges, so I use flight 2. I believe I can use, the only thing I want to set is I want to store the results on the score parameter. Remember, there was a parameter on the airports. So this is saying that Atlanta, ATL, is the most influential airport in the world, followed by Istanbul, Chicago O'Hare, Denver, Dallas Fort Worth. It means that they have the most incoming flights that themselves are coming from influential airports. So it's not just measuring the number of of incoming flights, but it's measuring the importance of those incoming flights. And that depends on, are the source airports themselves important? And so you can see these are realistic ratings. Atlanta is often considered the top ranked airport in the world, and PageRank confirmed it. So let's move on to the next algorithm, Louvain. Louvain is a community detection or clustering algorithm. And we're going to look for the natural communities of airports based on flights. We can take multiple vertex types. We just have one airport. We could take multiple edge types. We have just one. We're going to use the undirected flight route. And we do get to specify a weight on the edges, and that's miles. And we're going to want to store the results. What it's finding is communities. It's going to assign a community ID number to each vertex. And if you remember, the schema here, for each airport, if you look down at the bottom, there's a score and there's a community ID. So we're going to be saving the result in the community ID. Oops. And this warning message says the graph's size exceeds the limitation. The graph will not be rendered. That's just talking about the display of the graph. You can see the algorithm is actually already finished. It's just not visually showing the graph. We're going to scroll down to the bottom of the JSON because it's sorted with the largest community at the bottom. This means it has 4,494 airports out of about 8,000 airports. So that's more than half are in this one large community with ID of 0. You see the next largest one has 472 members. So it's only a tenth as big, and they keep getting smaller and smaller. And let's find one that's about 160 seems reasonable. Let's remember this ID number. And we're going to visualize it. So at Explore Graph, I'm going to open that up in another tab. And I'm going to filter by that community ID. So my condition, an equality condition, where it is an attribute called community ID, and it is an integer, and that value was 179. And I believe there were about 60 members, under 100, so we'll say 100. And there they are. If we zoom in, you see it just has the ID numbers. Those are hard to recognize. So let's go to the settings and add city and country. And now we see, okay, some of them still don't have a value. That happens when there's smaller airports. Philippines, Solomon Islands, Philippines again, Solomon Islands again. Let's keep looking. Papua New Guinea, Papua New Guinea. So we're in the South Pacific. And that makes sense that there are not a whole lot of flights going to the South Pacific, but within, among the islands. You know, there are a couple hub airports, and then you fly from the larger islands to the smaller ones. So this represents one of those communities. Let's try this one more time. Let's go a little bit larger community. This one has 96 members. And we just need to go here to the filter and change that value. Clear this out and display again. And now we see Finland, Iceland, Norway, Norway, Norway. Again, you see a geographic region, Poland, Denmark. So we're now Israel, but not the capital. So still Northern Europe, a little bit to the east, and again, another logical community. So the Louvain algorithm is finding those communities. So let me show you one more algorithm. Jacquard similarity. And in this case, I need a starter airport. So I'm going to go back here, and I want to pick one in the US. And what I'm going to do is I'm going to actually pick the one with the IATA code that is sort of my home airport, Canton, Akron. And let me clear this data. And what I did was, because see, CAK is not the full name, it's CAK-4112. And that has to do with a quirk with this data set that not all the airports, it has some small airports that don't have IATA codes. So there also has to be a supplemental number to give full information for the airport. So we're going to run this Jacquard similarity. And this is where I give that ID. And the edge type is flight 2. It also asks about the reverse flight. So reverse underscore flight 2. And I need to finish up because I know my colleagues are waiting. And if you scroll over, you see this is Syracuse in New York, Greensboro, North Carolina, Buffalo, New York, Savannah, Georgia, Dayton, Ohio, Columbia, South Carolina, etc. These are all in the eastern US. They're all secondary cities like Canton, Akron. So that makes sense that this was trying to find which airports are similar in terms of connectivity. So they probably have a few flights to an Eastern hub airline. So yeah, Canton connects to a couple of the Eastern hubs like New York and Atlanta. Similarly, these connect to the Eastern hubs, and that's why they're considered similar. So I want to thank you for your attention, and I am now going to hand it over to John.
Thank you, Victor. All right. So I'm going to be talking a little bit about machine learning graph enrichment and also doing some feature extraction. So as a data scientist and a machine learning expert, you're probably most likely extracting features. And we're going to talk about a little bit of how you can enrich your graph and with some features using machine learning, and then also how you can generate new features. So this is a project that the community and I tag teamed on. So when COVID hit, we had all of these research papers that were being generated. And so the Allen Institute of AI and the White House and some other leading organizations came together and issued a Kaggle challenge. And the Kaggle challenge was trying to figure out how to best present this material so that there wasn't an overwhelming amount of noise. And so the research scientists could be able to better understand what papers they should look at and what other papers are like those papers. And so I thought this would be a great use case for having it into a knowledge graph. And so we're just going to talk and use this as an example of what we can do with a knowledge graph in machine learning. So if you're not familiar with Google in 2012 created a blog called Things Not Strings. And that's when they declared to the world that they're using graph or semantically linking the data in the backend. So if you look on the right-hand side, this person searched for Matt, and all of a sudden, not only the listings of similar search results, but there's also books, there's people also searched for. So it was looking at the connections between this person and what's related to that person. Now at this time, this was probably using PageRank. I think they switched from PageRank in 2016, so I'm not sure what they're currently doing. But essentially what they're doing is scraping the web pages, then they have it semantically linked in a knowledge graph. And then from there, they're running an algorithm. PageRank, if you're familiar with Larry Page, PageRank was one of their algorithms from Google. And so that was one of the ones that Victor showed you in the previous section. So how is that useful in our use case here with the COVID papers? What we can do is we can take those COVID papers. So now we have a bunch of COVID papers, and they might have different entities and different things that they talk about. And so how do we extract those entities into vertices and edges? And that's what our challenge was, is that we have 65,000 papers, and we needed to then process these papers, pull out the entities that are related into these papers, semantically link them, and then try to better understand what the papers are about. So in this case, we're using a tool called SciSpacey, which is based off of Spacey, but SciSpacey is for biomedical text processing. If you're coming from the healthcare space, this is one of the models that you could use if you have like a nurse's notes, or if you're also doing a huge knowledge graph and doing biomedical literature with ICD codes and SNOMED codes, and you want to interlink everything together. So SciSpace is a good tool if you want to process some of that and enrich your graph with some of those external data elements and internal data elements as well, because you might have some benefits packages and things like that as well. So what that looks like is we have the Kaggle data. So we have all of these documents, 65,000 documents, and this is a very high level picture of what the flow was. But we have these 65,000 documents. We ran them through a machine learning model. So we're taking machine learning, and then what we're doing with the machine learning entities that were extracted is that we're modeling that inside of the graph database and semantically linking it to the papers. I know it's going to be a little bit hard to see, but this little purple node right here is the publication. And so if you hovered over this publication, what you would see inside the attributes would be a URL, so that that publication is actually public somewhere in the web. You have on the right-hand side an author, so an author published, and you might have multiple authors publishing the paper. The publication is also published in a journal. You have the publication has a license agreement to it. And then a publication has some of those entities that were extracted. And not only that, but we also had the entities belong to a class. So if you think of a class maybe as cancer, there's probably a bunch of different types of cancer that are in there. So if you wanted to look for papers related to cancer and a specific type of cancer, maybe you wanted to look for a paper that had I don't know, animals in it too. So you want to do animals with cancer and COVID. I guess you could search however you'd like to, but then we can introduce these graph algorithms into it. So now we have the data, we process the data using machine learning, we have it semantically linked, and now we can get really into some of those algorithms to determine the similarities. Maybe we want to use PageRank just like Google did and determine the papers that are most similar to this paper. Now this lab, I don't have a full walkthrough demonstration that we're going to be going through today. I do have it pre-recorded. So what you can do is watch the video at the end here and go through this lab. I have all of the links. So if you want to replicate this machine learning graph project, it's a very good way to get your feet wet into the machine learning, enriching your graph using machine learning. So some of the other things that are unique, so we just talked about how you can do machine learning and bring those machine learning things after they've been processed into the graph to semantically link it. But what if you're doing machine learning on your data and you want to generate new features? This is where you can use GSQL query pattern features. And so what you're looking at is the representation of a bad phone versus a good phone. So if you look on the right-hand side, there are classifications of what a bad phone is. And so you can see that there's a short call duration. So when there's a short call, that's one of the features that we're going to create. If there's an empty stable group, what that means is that the phone is not calling back consistently to a phone. Maybe there's no callback phones. There's many rejected calls, and then the average distance between phones might be less than 3. So you can start to use how your data is interconnected as features themselves for your machine learning. And then on the left-hand side, you can see what represents the good phones. You have high callback phones, stable group. You have these many in-group connections. So you called your mom called your sister called your dad. You could see that as a good phone pattern. And so you can create these patterns that you want to use for your machine learning externally. And we're actually going to be doing a Google Colab here shortly that you can follow along and do some feature extractions. And then maybe you want to use TensorFlow later on, but at least we'll cover out how you can extract data from your graph. Now, the other thing that you could do is that we now have the enriched data using machine learning. We have these patterns, but maybe we want to also look at creating new data from your data. And so this is looking at the patterns of data. In this case, we have a provider, we have a claim, and we have a patient. So a provider went to see a doctor. then there was a claim generated. That claim has a timestamp. Then they went to another doctor and there was another claim generated, and then there was another timestamp. So if we can infer that, okay, they visited this doctor and then directly related to that with the same patient, sort of the same similar use case, we can get that referral or referred by a connection as well. The easier way to maybe think about it is if we have a person vertex and then we have a relationship called father. You think of John and his father's name is Larry, and then Larry's father is named Larry as well in my case. And so even though we don't have an edge called grandfather, we could infer that my father's father is my grandfather. And so that's sort of what this is doing here, is that you're actually generating new data with your existing data as well. And so you can start to explore these different things to create new features, create new pieces of data. Now, this is the lab. So if you wanted to get your hands on and run through the machine learning graph enrichment, so using that size spacing model, we have all of the workshop files on the cloud. We have the TG Cloud link. We have I think it's actually in Google Drive. And then we also have the video walkthrough. So this will walk you through every single step of that demonstration I just talked about. On the right-hand side, we have an API launcher. So we talked about size spacing. There's a couple different other models that you might want to use. This API launcher will actually launch the model. It's using Google Colab. It's using, I believe, Flask, and it will launch that Python model so you can do some data enrichment. On the right-hand side to the top here is the UI that we created in the community. So it's basically looking, it just looks exactly like Google. It's pretty simple. You have an input field, and then you have a search button, and then it's going to search for similar articles based off what you inputted. And so essentially this lab walks you through how you can create your own Google on top of these medical papers. So the next part, what we're going to talk about is doing feature set extraction. So now that you've generated new features, you've maybe used an algorithm, or you used the data enrichment techniques, or used a certain algorithm that determines a new feature. You can now that you want to take that data and you want to extract it. And so we're going to do a little Python notebook. If you have TG Cloud open and you have your cloud instance still open, you can follow along. I will put this link right now, and let's see if I can copy it into the chat. And what you can do is, what you want to do is actually save a copy of it. So I'm going to put it in chat for you. And just to give you a little bit of background into this data that we're going to be looking at, this was from FinCEN. So this is a bunch of activity around financial data that a bunch of journalists and reporters were come together to collect all of these transactions and try to find a fraud. And what we're going to do is take this data that they have in the CSV files. We're going to use this notebook to actually generate our graph. And then we're going to extract some features on the fly. So if you have your TG Cloud ready, so you want to make sure it's ready. And then you also, if you don't remember your domain that you created, you can simply go to this application and click on Graph Studio. And this will bring you to the domain, because you'll want to have your domain when we use this notebook. So if you have the notebook open, what you can do, I'm just going to reconnect, is you go to File, you want to save a copy. So this will be your own copy. You can use it. You can refer to it later, and you can use it for this demonstration. So the first thing we're going to do is use this TigerGraph. And the specific packages I'm going to use is TigerGraph Beta, because what we're doing in the beta version is removing all of the Java dependency on the GSQL client. We're using pure Python, which will just speed up the process of executing GSQL queries. So now that you have your instance up and it's ready to go, the next thing I would do before I even get started is you want to copy and paste that URL in right here. So if you looked at your Graph Studio, you see that the URL is right up here. What you're going to do is copy that URL, make sure you input it here. The next thing you're going to want to do is, if you remember your password, so you had to remember your password when you created the cloud instance, you're going to put your password right here. Your default username for the free instance is called TigerGraph. So now once you have all of those things good to go, don't hit play yet. Why I say that is because you probably have your old box still up, right? And it has the old data in it. So what you're going to do is go all the way to the bottom here. And for those folks that have a existing box up and it was maybe using that algorithms starter kit, what we're going to do is clear that box. We're going to remove all of the we're going to remove all the nodes. We're going to remove all the edges. We're going to remove all the data. We're removing everything. So if yours is commented out right now, I know one of the older links might have had this commented out. All you want to do is uncomment it and then run this by hitting this play button right here. So I'm going to quickly hit it. And as I said, it's just going to go through and clear out everything. So you're going to literally have, I think actually mine's already clear. So you're literally going to have this. You're not going to see anything. When you click on here, you're not going to see any graphs, even if you did use a starter kit for the previous section. So we can see that we dropped everything now. So that's good to go. I usually just like to comment this out again, because sometimes we might get ahead of ourselves and just, run all, and we just want to make sure we don't run everything and then drop it. So we're going to comment that back out, and we're going to go back to the top here. So let's get started. So now we want to basically grab that package and maybe grab some of the other dependencies that we're going to be using. We're going to be filtering some of the data out, and you can just hit this play button to get started. So you're going to see everything's going to be fetched. It looks like I actually ran this, so mine already says requirements are already satisfied. What yours will probably say is that it just downloaded, and it'll show you the latest version. So the next thing you want to do is set up your connection. So now that we have our packages, we're going to set up our connection to our TigerGraph box. All right, I think this ran so fast that I didn't know it ran, so it's okay. The next thing we're going to do is grab the data. So the data that was from the FinCEN is located in GitHub. So we're actually going to clone the GitHub repository into our files here. If you wanted to go over here, you can see them. So when you clone them, you'll actually see your files being generated and put into this environment here. So hit play. Mine already exists, but yours will just load them here into the folder. So if you want to check to see if they're actually there, you can just see them right here. So we're going to go to the next step. Now, traditionally, you might have some data, but some of the data is not clean. And so what you're actually going to do is do some data cleansing. You don't want to have dirty data into your graph. Maybe you want to reformat some of the date times so they're standardized. Maybe you want to remove certain parts of attributes. You want things to be uppercase, lowercase. There are different techniques and different standardizations that you might want to abide by. And that's where it's important to make sure your data is clean. And so right now what we're doing is taking that data, we're cleansing some of that data. And you can see here, I remove some of the nulls as well, or the NAs, and replace that as well. So, okay, at this point, we should have our data here. So if we want to just test and see what our data looks like, we have the data frames. And so this is pretty standard. This is all just no graphy stuff yet. We're just looking at data. We're looking at some data frames. We're trying to understand our data. And then what we might want to do after this is actually create our graph. So we're just going to test here to see all of our data frames. So they look good. They look good, and they look good. So the next part here, what we're going to do is create the edges and vertices, and the way that this looks in the graph, we'll go to it as soon as I run it. But what we're doing is defining this actually on a global level. And then what we'll do is we'll create our local graph called FinCEN and take all of these vertices and edges that we created and put it into this FinCEN graph. So you can see here that I did look at this data above here, and I wanted to, okay, I see that there is a filer, so there's an organization, there's some banks, there's some countries. And so I took this and then created a schema around it. So next, what you can do is just hit the play button, and you can see that we have the vertex type organization is created. So all of this has just been created. It's been passed through the GSQL endpoint. What we're going to do then from here is I just want to sort of explore. Hopefully I can see it when I just refresh. Let's go to design schema. there we go. So we had nothing, and now we can see that our schema has been created. So we have an organization filed, a filing. An organization has a filing, and then there's a filing beneficiary, and then also organization. So it's pretty a pretty simplified version of a schema, but it will be it'll be okay for this demonstration. We don't need anything too advanced. So after that, let's actually create our graph. And so we're going to use the GSQL endpoint again. This is our GSQL function in TigerGraph. And what you can do then is you can execute some of these GSQL functions that maybe you'd usually do in a terminal. You can inject them directly into your instance. So in this, we have a create graph called Finson. We're taking these global vertices and edges, and we're going to be putting them inside of the graph. So we'll just hit play. And this might take a second here. Okay, it was faster than I thought. But so now we created a local graph here called Finson. And what we're going to just do is test to make sure everything looks good. So ls is just a command that lets you see what's in the graph. And so we're seeing what's in graph Finson here. And we can see all of the things that we created the graph with are up there. So the next thing I want to do is update some of my parameters. This is the backend parameters that we gave it, the username and password. I also want to give it the graph that I'm going to be working on. And then from there, I'm going to generate a token so I can do some, do some queries and different things with it. And this is where you just hit the play button. It will take care of this all for you. All you have to do is insert your graph. So this might be, this might be something. If you're trying to run this outside of Finson, you want to update this according to your graph here. So now we're going to get to load data. One of the unique elements of, it wouldn't be a good Python connector if it didn't know how to take data frames and upsert it. So natively, TigerGraph uses JSON to upsert. What we're doing is we're looking at the data frame, converting it into JSON, and then upserting it for you. So we can take our data frames and then upsert them into the graph as well. So let's see, we're adding the data right now. And what we'll do is quickly look at the data just to make sure everything looks good. All right, it says all of the data has been uploaded. I'm just gonna go back in here. We're gonna go, I have to refresh. All right, so we see that the graph was created. We can see it here. We can see load data. We can see that we have data, perfect. All right. So this is the last part. So we've created graph, we have a graph, we have the data, we have the edges, we have everything there ready to go. And then what we want to do is maybe do some feature extraction. And not only just extracting the features that are in the graph that are created, maybe we used our machine learning techniques, maybe we used the enrichment techniques, maybe we used these algorithms that Victor has talked about. We can also create features on the fly during the time of execution. And so you can see here that I'm doing these accumulators. And so what I'm doing is accumulating the total transactions. I'm going to find the max transactions and the minimum transactions. And then also do on the fly calculation for a sum of all of the account. I think this is just a count filed. So how many filings were there? And so I'm doing these on the fly. So these aren't features that actually were generated, or these features are not actually in the graph. We're going to be generating these features on the fly as this is executed. And so this is a pretty basic query. We're going to start at organizations. We're going to go look at their filings. We're going to then use our accumulators that we defined up here, and we're going to then print everything out. So let's get, and there we go. So this is called an interpreted query. Most times when you're putting stuff into production, you want to install your query. That will compile it and create an endpoint. Interpreted query will just let us run our queries on the fly and give you back the results. And so you can see here that we printed off, we ran this query, we executed these on the fly, and now we have those calculations. So now if you're using your machine learning models and you're creating new models based off your data, you can use all of these new feature things that we just talked about today and to enrich your machine learning models and make them better. If you wanted to start this lab over again, all you have to do is drop all, and you can start this from the top up. All of these files, labs, everything are included in the slides, and the slides will go out to everybody. And with that, that ends my section, and I'm going to pass it on for part 3.
Hey everyone, I'm Monal and I'll be starting with part 3 of this. Just give me a second to share my screen. Yeah, I would be covering is the in-database machine learning for graphs in this section. So to begin with, I'll start by explaining what's the difference between in-database machine learning and the traditional machine learning techniques. So as John already mentioned that what he demoed was that he ingested some data to TigerGraph and then he ran a query using a Python script to extract the features from the graph. So that's basically the traditional machine learning pipeline which are used very frequently. So here there is an example that if we have any recommendation system on an e-commerce website or any similar websites, uh, what happens is that it has an ACID transactions with a database for requests and results, but all the machine learning aspects or the model training for that recommendation happens outside of the database, so that we fetch the training data, train our model, and return the results back to the database, and that's when this application can run and use machine learning data. So uh, that gives a very efficient approach, but it's not a real-time system. And to scale that real time, we need a lot of data engineering pipelines to be built to grab the data from database and load it into the machine learning platform and then load back to database. So here, what we are proposing is that we can do is in database model training. So this is basically possible because TigerGraph is built on massively parallel processing architecture. So it can scale and it can run all these algorithms in parallel so that we can achieve these real-time results from database itself from the machine learning models. So one of the primary aspects of doing this is that there is no need for exporting any data outside of database and then loading it back in. So that's less hassle of data engineering aspect there. And then you can, as I mentioned, that this can be real time. You can continuously train and evolve your model and feed it to your applications. It has less limitations on model size. So because it's an entire database, you can train and split your data accordingly and then run your models on that. And as I already mentioned that with TigerGraph, all this can be done in distributed system. So it gives you the speed to have your data processed and loaded into your applications much faster. So to go over an example in this, I'll take user rating movie graph. So here in this example, it shows very simple graph here that we have two movies, Toy Story and Iron Man, and we have two users, Alice and Bob. So for doing this kind of movie recommendation systems, we can use is multiple techniques. So some techniques are memory based, while some are more of machine learning model based techniques to predict the recommendation links. So one of the primary methods used is content based methods. So in the content based methods, uh, what we do is like here we see a lot of metadata associated to this user and movies. So we know that Toy Story belongs to the Disney platform, Iron Man belongs to a Marvel platform, And we know that Alice likes Disney and Marvel movies. So we can say that if Alice likes Toy Story, Alice would also like Iron Man. So that's a content-based uh, recommendation that if we have all this data rich feature set, we can use this method to predict or recommend new movies to users. But what if we don't have this feature set? What if we just have users, movies, and their ratings? So there comes the second method called the KNN or K nearest neighbors. So here our data, we have Alice with a rating of 5 for Toy Story and Bob with a rating of 4.5 for Toy Story. And we know that Bob has rated Iron Man as well with the rating of 5. So now, based on this first two links that both of them have rated Toy Story as a high rated movie, we can predict or have this link added which says that K nearest neighbors, using K nearest neighbors, that Alice might also like Iron Man. So that's the second method. Again, both of these methods require a feature set because here we know that Bob has rating for both the movies. So that's a memory-based feature set which helps us recommend movie to Alice. But what if we don't even know if Bob likes Toy Story or not? So in this kind of cases, we need more of a machine learning model here, uh, which can be trained to recommend movies to the users. So here, what we are going to discuss in this talk is the latent factor model. So latent factor will help us determine what are the good recommendations for these users and how we can use this machine learning model and train it in the database itself. Also, you can use these hybrid or ensemble models where you are combining this content-based and model-based approaches to recommend users with the movies. So here I have my data set. So this data set consists of movies and users. So I have 6 movies, 4 users. The movies have two genres. So one is they are romance movies or they are action movies. And for the users, I have rating for all of these movies as well, wherever it's available. So here in this latent factor model, first we will generate is latent factor vector for each user and each movie. So this latent factor vector consists of, here we have two genres, action and romance. So it consists of that the first part of the latent factor vector is associated to the romance movies and the second index is associated to the action movies. So that's the rating. And theta is the latent factor vector for the user and x is the latent factor vector for the movies. So how do we come up for this latent factor vector values? That's what I'll cover a bit later. Uh, as of now, you can see it was generated by the model training, and this is what we came up with. So when you try to do this latent factor model, what happens is that you take this vector for a user and have a dot product with the vector for the movie, and those results of the dot product are our prediction values as a result of the algorithm. So when we do a dot product of this first vector 50 with 0.90, we get 4.5 as the prediction for Alice liking the movie Love at Last. So that is a pretty close prediction here. That happens similarly for all the other movies. And when you see that how that works, so we first created this latent factor vector for user and movie, and then we predicted using a dot product of these two vectors. So as I mentioned that the first part or the red, all the highlighted values in red are for the romance genre and all the highlighted value in blue are for the action. So here we can see that Alice likes more of romance movies than the action movies. So when it comes to action movies like, let's say, Sword versus Karate, it gives the prediction of like Alice liking that would be 0.5, and overall it's 0. So that means the action movies are not preferred choice for Alice, and that should not be recommended there. So now coming back to the model. So for this latent training this latent factor vector model, what we'll do is we'll first need a cost function. So our cost function is a function of all the user and movie latent factor vectors. And then what we do is we first calculate is the root mean square error here. So our root mean square error is calculated based on dot product of these two latent factor vectors subtracted from the original prediction value, original rating value which we had. So that's the root mean square error. And then we are adding is regularization so that we don't overfit our model to return the movie recommendations. And in the regularization, lambda is the regularization factor by which we are running this algorithm. The formulas after that are the gradient descent for this particular algorithm. So when we try to calculate root mean square error along with regularization, our algorithm might never converge to return any results based on their rating. So to have that, so that becomes an optimization problem. So to have that algorithm better optimized, after each iteration or each epoch, we'll need to do is recalibrate our latent factor vectors for users as well as movies. So as I mentioned earlier that I would be coming back on how to calculate this latent factor vectors. So what our algorithm will look like is that first we will have a random number generator for calculating this latent factor vector, and then we'll calculate the root mean square error and regularization for that particular user and the movies. And if our error is really high, we'll go to this gradient descent. So what will happen is that this gradient descent will recalculate the latent factor vector, and that would be the latent factor vector which we'll use for the next epoch. And to do that particular procedure, what we can see here is that each user is dependent on its rating to the movies. So here we can see user 1 has a rating Y11 to movie X1, and also rating Y12 to movie X2. So given this kind of connection between user and movies to do the gradient descent or have this kind of latent factor vector generated, it makes it very easy for a graph problem and a graph database to resolve this and run it in parallel. So here is the model training in graph and how it works. So the formula here is to calculate a gradient for a particular user. So a gradient is basically drop this dot product of the latent factor vector between a user and a movie subtracted from the actual rating, and then we again have a product of multiplication or a dot product to this particular movie to this movie latent factor vectors. So what happens in the model training is that we'll first collect all the latent factor vectors for the movies and all the ratings for those movies. So that's xi and yij from all the movies. So here, as you can see, we have collected it for both the users. Now we'll compute the gradient contributed by each movies. So here, using this formula here, we'll calculate gradient by each movie, and you can see it on the screen that how that is calculated. And then in phase 2, as you can see the summation sign, so it aggregates all these gradients for a particular user, And once all these gradients are calculated for a particular user, we run the gradient descent, which we saw in the previous slide, to generate or to recalculate the latent factor vectors for those particular users. And we run this kind of process until we have reached a very less root mean square error, where we can say that our predictions are better for this or similar to what actual ratings on our training data set. So as all the machine learning procedures, this running this in graph database itself also has similar kind of structure. So first we'll do is split the data into training and testing. Then we'll initialize the latent factor vectors. And then we'll calculate the difference between prediction and label. So that's our root mean square error. And then if we see our error to be less, it will be converged and our algorithm will be finished. But if not, then we'll update the latent factor vectors using the gradient descent and try to recalculate the latent factor vectors and the prediction so that our root mean square error reduces and we are able to converge the algorithm. So I'll go over the one training block of this query, and then we'll see the demo on the TG Cloud. So here in the training block, we can see that we have this data. So first of all, as we had in our training phase, that we'll collect all the movie and rating values for a particular user. So that's our this select line that select all the users which has a rating to any movies. Then it goes to the accum block. So accum block in GSQL is basically processing all the edges separately, and while processing all these edges separately, it does it in parallel. So all these edges are processed separately in parallel, which gives it which is basically like a map reduce process that it processes everything and then it reduces in the post accum. So if you go to accum, we are calculating the prediction delta and the gradient for each user and each movie. And then, as I mentioned, that it's basically similar to MapReduce. So all that happens in parallel, and then it goes to post accum, where we calculate the final latent factor vector for each user and movie. So that's one of the GSQL training block. And now we can go to the demo of this particular on the TG Cloud. So on the TG Cloud portal, you can go and select is that's this in database machine learning recommendation v3. So if you select this starter kit, you would be able to go and launch it. And as I've already done it, this is what you'll see. So there will be a global view and then a recommender graph. And then when you go to design schema, you'll be able to see the schema. So it's a very simple schema that we have a user with its primary ID or the user ID and a theta, which is the latent factor vector for that user. And then we have a movie with the movie ID, name of the movie, and average rating of that movie. And then X is the latent factor vector for that movie as an attribute. And then we have an edge called rating. So that rate has the rating between a user and a movie, and there's a label that it's present or not. So oh, it's not running. Yeah, it will take a couple of minutes to start so that I can, let me go back to the slides. Yeah, so going back to the slides, there is, as we saw the GSQL training block, this training block will keep on running in the graph until we converge the graph database, or we converge the algorithm, or we have a properly defined total number of epochs which we want to traverse through. So here what happens is that in GSQL you can do loops, or as well as limit those loops to particular number of epochs, and then you'll get the results there. So yeah, it's not in this query, but I can show that on the cloud. So here we have these two files. One is the rating file. If you click here, you can see that I have user ID, movie ID, and rating. And then there is this movie list file which says we have movie ID and name for that particular movie. So these are the two files loaded, and this is how the data is ingested to this particular node. So we have this edge which says like user ID goes to this user ID in the user node, and then this again movie ID goes to the movie ID node, and then using the movie list we populate the movie names, and here we have the ratings. So as you can see that here in the user node there is theta, and in the movie node there is average rating and the latent factor vector which are empty. So that is something what we'll populate using the GSQL queries. So here you can see we have 1682 movies and 944 users and around 100k rating edges. So if I go to explore graph, I see these movies and users, and if I go here and expand, so I see are these graphs where each user has rated to these particular movies, and we see their groups. So now when you go to this GSQL queries, you'll see a README file. So this README shows about what queries to be run in what order or sequence to get the training done and have the recommendation for a particular user. So as it says, like first go to the split data. So this split data does is it splits the overall edges. So that's the user rating edges of 100K into two parts. So training and validation with a 70-30 split. So if I click here, then these are the total edges. And then we have 70% for training and 30% for validation. So after that, we do is we go to normalization. So what this normalization query does is it generates the average rating for a particular movie, which we have already set as an attribute as average rating. So when I click on this, it normalizes all the queries, all the average rating for all the movies. And once we have normalized that, we'll need to do is initialize the latent factor vectors. So as I mentioned earlier, that these latent factor vectors are the random numbers generated, and then we try to update those after each epoch using gradient descent. So here, what I am using is a Gaussian distribution to generate these random numbers. So this is the random number generator function, which is multiplied to standard deviation, and then mean is added to that. So as you can see that 0.1 and 0.1 are the inputs or the arguments which we are passing to the query to generate these latent factor vectors. So I've generated this latent factor vectors. So when I go back to now explore graph, I can see for this user that theta values are populated now. So that's the latent factor vector. And here for the movies, I can see the average rating as well as the latent factor vector values. So once I have this ready, then I'm ready to train my model. So this is the query which trains the model using the latent factor. So um, when I run it, I have to pass in is the learning rate and the regularization factor, which we saw earlier in the formulas. And this is the iter is the total number of iterations or epochs we want our algorithm to run. So when I run this, it will take a couple of seconds to finish. So as you can see, the output of this training is the RMSE, that is the root mean square error for the training set and the validation set. So here, initially the training error was 1.0 and the validation error was 1.05. But as you can see over the period of 100 epochs or 100 iterations, you can see there is a change, or the training error or the validation error has been in less than 1. So that has reduced. So we can see that our algorithm is working well and our model has been trained. So once that is done, we can do is test our model. So I'm running the query and I'm saying the user ID 1. So for this user, I'm seeing is that predicted ratings for this particular user. So for this movie, the real rating was 0.09 and the predicted rating using this query is 0.1. That's similar to all these movie ratings where we can see the prediction here. So yeah, this is not a very good example. Let me look at another one. So here again, the real ratings are like in negative, but I'm also getting the really small predictions of 0.1. So this is kind of a bit similar predictions in some cases. In some cases, it's not. But that depends on the number of training sessions and the epochs which we can train on. And also there is a query to run the recommend query. So if you type in the user, let's say whatever we did, 252. So these are the movies recommended to that user with the predicted rating. So basically these are the queries which you can see and run using our TC instance. And I'll now go back to the slides. So here we have this instructions on how to go and run the starter kits. And yeah, so this is where you can start with TigerGraph Cloud and have all the latest information using the community or social media. And yeah, I think I'll open it for the Q&A session if anyone has questions. Also, yeah. Also, you can reach out to any of us, Victor, John, or me, if you have any further questions on this.
So thank you to our audience. You've sent in a lot of questions. There's one that I already answered in chat, but I wanted to bring it up again to make sure everybody caught it. And there are two more. One was, is it a benefit to implement machine learning training in GSQL compared to leveraging existing machine learning training models? And so my response was that in database machine learning in general, so traditionally the database is just where you store your data and do more basic querying, and more databases are offering in database machine learning. And the advantage, of course, is that you have the most current data, and that you don't have to export and import the data. If it's large, the amount of time and possibly expense to have that other information another system, excuse me, another system where you will do that outside computation may outweigh the benefit of doing it elsewhere. So it's a trade-off. And there's some sort of incremental learning techniques that actually can take advantage of evolving data. So for graph in particular, there's some new graph neural networks and graph embedding techniques where you do need the graph structure, you want the graph structure. So whether you're doing it in the database itself or an external copy of your graph, you need the graph structure. And just doing it in database saves you the trouble of having to deal with that export and operating that other system. So it's a trade-off. TigerGraph has the performance characteristics and the GSQL has the programmability that this is a viable option, and it's ultimately it's up to you. Second question, like to understand more about graph modeling and machine learning applications. Can you suggest some references or books? For shorter references, we have lots of blogs on this topic. There are some introductory books on graph databases and graph analytics. I will point out they tend to be by vendors. So there is maybe some possible bias. You know, there are some nice introductory books from some of the other graph database vendors. I will mention that TigerGraph and I in particular am working on a book on advanced analytics and machine learning with graph, and the first couple chapters will be available for sneak preview shortly. I'm gonna let some of my colleagues read off some of the other questions and try to answer them if they're ready.
Anil, you want to go first?
And we are at the hour and a half. We're going to stay online to continue answering questions. We're sorry if some of you have to leave, but you know, I think you can contact us individually later, but we're going to stay online to answer questions. Let me read the next one. Have algorithms for probabilistic graph models, i.e. conditional independent structures, been implemented through TigerGraph? So I assume that what you're saying is some of the edges, the connections, are probabilistic, that it's not a certainty that the relationship exists. So there's a probabilistic weight. There definitely are algorithms for that. Like I said, we have some graph algorithms that use weighted connections. We have some customers who have implemented. I don't think we have a detailed use case, but that's a great suggestion to do that. There's another question about conditional random field algorithms been implemented. Again, we don't have anything in our library right now. Again, if you'd like to send a specific request of what you'd like to see, you know, Manil is on the development team that works on some of those, so we'd be happy to take your suggestion. I see one more new question. Are there more use cases with real-time demands and FPGA hardware hosted databases? Interesting that you mentioned FPGA, because we have a partnership with Xilinx. They've developed some solutions for some of our algorithms, cosine similarity, Jacquard similarity, which I demonstrated today, and Louvain, which also I demonstrated. So some of the ones that I demonstrated, if the native platform isn't fast enough for you, you can get hardware acceleration through Xilinx. So glad to answer that. Any more questions? As I said, we are over time. We want to thank everyone for attending. You will receive an email with a link to the recorded webinar, and we want to thank you for your attention. And come see us online in the community or our main website, and see you next time.